Big data storage. The key requirements of big data storage are that it can handle very large amount of data and keep scaling to keep up with growth, and that it can provide the input-output operations per second necessary to deliver data to analytical tools. The largest big data practitioners are Google, Facebook, Apple, which run on a well-known environment, the hyperscale computing environments. These comprise vast amount of commodity servers with direct attached storage. Redundancy is at the level of the entire compute storage unit, and if a unit suffers an outage of any component, it is replaced wholesale, having already failed over to its mirror. Such environment run the likes of Hadoop, NoSQL as analytical engine, and typically have PCI's flash storage alone in the server or in addition to disk to cut storage latency to a minimum. There is no shared storage in this type of configuration. Hyperscale computing environment have been the preserve of the largest web-based operations to date. But it is highly probable that such compute architecture will bleed down into more mainstream enterprises in the coming years. The appetite for building hyperscale systems will depend on the ability of an enterprise to take on a lot of in-house hardware building and maintenance, and whether they can justify such system to handle limited tasks alongside more traditional enterprise environments that handle large amount of applications on less specified systems. But hyperscale is not the only way. Many enterprises and even quite small business can take the advantage of big data analytics. They will need the ability to handle relatively large data sets and handle them quickly, but may not need the same response time as those organizations that use it push AdWords out to users over response time of a few seconds. So the key type of big data storage system with the attributes required will be often scale out or clustered NAS. And the other storage format that is built for very large number of files is object storage. Properties of a big data storage architecture. So what are the properties? We will be discussing it one by one. Big data is a big deal because it offers answers to the questions that were previously unobtainable and insights into the behavior that can provide the foundation for better products and services. By algorithm crunching big data, distilling it, enhancing it, analyzing it, visualizing it, business are getting a big advantage. So the very first characteristic is be scalable. Of course, any big data storage system must be scalable, but how scalable? What capacity will your requirement need? Expert says that in an ideal world, you would answer this question by dividing the data and application into the categories, creating a predictive model of capacity needs for each category based on expected growth and aggregating the results. However, it requires significant staff time and therefore isn't realistic. Most of the time, there is usually one major application deriving most of the company's data growth. And this application usually facilitates the company's primary revenue generation or mission. Understanding and planning data storage needs for this application generally tells you the scalability you plan for. Then the question comes, what is the plan to achieve scalability? Here is a plan many storage vendors like buy one more disk. Essentially, what many companies are doing now, the bill for that strategy is both capital and operating expense get large quickly. The problem with simply adding disk is that this model isn't scalable in a number of ways. Scalability is not just about the size of storage, it has wider implications. The throughput and the speed of access must be scalable. In addition, the system should be able to scale operationally, that is to grow quite large without a huge increase in a dedicated staff. Moving on to the next characteristic is tiered storage. When it comes to providing storing and retrieving data, the first question is, how long can I wait to get the data I need? However, you also need to factor in the cost of storing the data on different tiers. An optimal big data storage architecture stores the data you need and archives what you don't need right away at the lowest possible cost. The best systems support a life cycle that provides a home for data flows in each stage of the life cycle from creation through archiving. Here is the hierarchy of storage methods. Flash, the fastest and most expensive form of storage. Spinning disk. Cost drop considerably, but excess speed is lower than the flash. Tape, The cheapest and most durable long-term storage. Much slower to access, particularly if the tape is stored off-site. Of course, not at all data will fall into one tier, and not all data will stay in one tier for its entire life cycle. In addition, the right solution doesn't have to support all the tiers. A mature solution for big data storage will allow data to reside in tiers and gracefully migrate from one tier to the next and back again as required. This is especially important because the relative cost of each type of storage changes significantly as technology advances. The key question is, what is the plan for the right storage and the right architecture for each type of content as it ages? Another characteristic is widely accessible content. Just as the increasing value of big data has made high availability a critical factor, it has also driven the need for content to be widely and quickly accessible as more users want to leverage the data to extract value. Often, these users are geographically dispersed and can even include suppliers and partners. As a result, distributing data geographically so that it is closer to users has become more important. In fact, experts say cloud storage is as much providing wider access to data as it is about outsourcing the management of their data. Another characteristic is analytical and content application support. In the past, almost all the data companies had to deal with was records in the database. Each unit of data was small, and the trick was sifting through huge collections usually stored in a SQL database to find the records you wanted. But in the modern world, the analysis model has been dramatically extended. Some of the most valuable analysis being done these days is massive parallel analysis of big unstructured files, whether huge web logs, financial data, or sensor information. In some cases, this is the same data being shared by human users in a content management application. However, the data performance requirement for these two uses are dramatically opposed. The best performance for human analysis requires an extreme service level for delivery of a single file or a set of files to a single user, so that even the most granular high-performance data set can be delivered with the integrity, while the best performance for computational analytic environments are instead reliant on the simultaneous movement of many streams of data. Video surveillance is a classic example of this challenge. Human users need to see the entire picture captured by the camera, while computational analysis slices each of these frames in the same video into tiles that all need to be fed into analysis engine in parallel for data integration. The ideal big data storage should be able to manage both the use cases in a single shared architecture. The next we have is the self-managing. Modern storage is always shared by multiple applications and the users. Some applications such as media asset managers are intelligent enough to automatically migrate data between the tiers of storage. But most applications do not have this capability, or if they do, storage administrators cannot use the functionality because a particular application priorities are in conflict with the another set of applications or the users. In this situation, it's critical for the storage system itself to be able to manage the tiering of data across the range of media types noted: flash, fast disk, low disk, and tape. Storage system almost always have many users. Most of the time, those users will be applications that are placing data in some type of storage and alerting the system when data need to be moved back and forth between the tiers. This sort of communication is hardwired into the application via APIs. The app tells the storage system what to do, but there will be many other ways that data will arrive and flow back and forth through a system. There may be policies for how long data is kept in the faster storage before being moved to the lower storage, including when the time limit or the size limits trigger migration. For example, data that hasn't been accessed for the 90 days may be moved onto the disk to tape, and older data that is suddenly accessed multiple times in a few days might be moved from the tape to disk. It is vital that as much of this activity as possible is easily programmable and automated. If it isn't, then growth in the storage means significant growth in the staff. A mature big data storage system will have an interface and appropriate automation tools for each of the user. Another characteristic is ensure content is highly available. as data-sized information stores increasingly become a key source of business advantage. There is a corresponding desire to keep this data forever while ensuring that it is highly available. Customers need to accomplish this objective without growing administrative or backup staff at the same rate data grows. When architecture storage leverage their internal policy engine to automatically make the copies of newly stored data across media and sites to ensure basic data availability on top of traditional RAID architectures. But as data growth continues to outpace traditional approaches, this availability model is being challenged, particularly in customer environments that required complete reliance on disk storage. Unfortunately, with traditional RAID-based disk architecture, as the density of data per disk, per storage channel, and per storage system grows, the risk of data outage and time to rebuild in the event of an outage increasing significantly. Another characteristic factor we have is the support workflow automation. Smaller unstructured data, typically end user productivity file, is typically for the use of single users. Big unstructured data is almost always driven by a set of data sharing application. Big data must be delivered to user in context of a workflow, the faster of information from application to application and user to user. For this reason, big data storage architecture must support easy integration workflow. This may include a specialized professional application such as Content Asset Manager, a laboratory information management system, or a broadcast information system. Whichever option the customer selects, the big data storage system must be ready to accommodate it. For this reason, the policy engine and functions of the system must be capable of being driven by more than system own internal policies or user interface. Another characteristic is integrate with the legacy applications. With the dramatic changes in both the big data requirements and technologies, the customer needs the ability to leverage the latest big data technology. However, frequently vendors offer these technologies only if the user is willing and able to forklift upgrade his or her prior system. Customers deserve a better productization experience than the offers. It should come as no surprise to anyone in the industry that customers, particularly large enterprise customers with a wealth of legacy applications, need the industry help in continuing to leverage legacy infrastructure, data, processes, and people skills as they migrate to new approaches. A well-designed big data storage system is heterogeneous and flexible, allowing for utilization of existing system and people. It should also offer interfaces that allow customers to utilize new big data storage functionality without the need to rewrite storage interferences. Another characteristic we talk about is enable integration with the public, private, and hybrid cloud ecosystem. Many of the storage tiers mentioned so far are going to be profoundly influenced by the cloud. It is possible to imagine huge network of cloud-based computer memory, banks of flash drivers, and wide storage. Moving data to and fro from the cloud is crucial. The ideal big data storage system must be built from the ground up to cloud enabled, not only for public cloud, but also for private and hybrid cloud environment. Be self-healing. The largest scale website and application, those created by the Google, Twitter, Facebook, and Amazon, all have the built-in ability to handle the failure. When a server in the cloud environment fails, there is no apparent outage, and this particular server is never fixed. Work is automatically redirected to another resource, with the failing server automatically taken offline for data removal. A well-designed big data storage system must work in exactly this model. It must accommodate component failure and heal itself without customer intervention. How big data is relevant to multiple verticals? Is big data relevant to me? What are these industry scenarios that could be benefited from big data analytics? Here are some of them. Financials. Fraud detection. Banks and credit cards are monitoring spending habits on a real-time basis. Customer segmentation applies in every industry from banking to retail to aviation to utility and others where they deal with the end-to-end customer who consume their products and services. Customer sentiment analysis. Responding to negative brand perception on social and amplify the positive perception. Sales and marketing campaign. Understand the impact and get closer view of customer delight. Call center analysis. attempt to take unstructured voice recording and analyze them for content and sentiment. Another industry is medical. Reduce readmissions. How to build a proactive follow-up engagement with patients. Patient monitoring. How to track inpatient, outpatient, emergency visit, intensive care units, etc. Preventive care. Disease identification is very crucial business function for medical. Claim fraud detection. There is no precise dollars that one can put here, but this is a big thing for a medical field. Another vertical is insurance. Fraud detection and analysis. Pricing based on the customer. Sentiment analysis, loyalty management, agent analysis, customer value management. Retail. Customer sentiment analysis, customer care centers, and campaign management. Supply chain analysis. Every sensor can be tracked for warehouse space optimization. Location-based marketing. Based on where a check-in happens, retail stores can optimize their marketing. Another vertical is telecom. Price optimization and plans. Finding customer churn. Customer loyalty programs. Call detail record analysis. Network optimization. User location analysis. Customer behavior analysis. This list can go on to the other areas like utility, manufacturing, travel industry, etc. So you can see there are obviously interesting facts that how big data is helping multiple industries in a multiple ways. These are just the representative list for our understanding and to correlate how big data is helping the multiple verticals of the industry. Now next, we will move on to the Hadoop.